Thank you for the introduction. So I want to talk about improved phase factor determination in quantum signal processing. This is joint work with my colleague Christoph Sunderhoff. We're at Riverlane, which is a quantum computing company based in Cambridge in the United Kingdom. So in the first instance, I'm talking about quantum signal processing, which is a framework for implementing polynomial functions via quantum circuits. And quantum signal processing, or QSP, initially applies to scalars, but it's significantly extended by the quantum singular value transform to apply to matrices as well. Only certain polynomials are implementable via this framework, and moreover, if you're given some polynomial, determining the sequence of unitaries needed to implement it is non-trivial. So a key step in this process is determining what's called the complementary polynomial, and I'll define what this is momentarily. But the main result I want to communicate in the talk is a general and explicit construction of this complementary polynomial that you need to apply QSP. So the most pertinent formulation of QSP, the one we'll use, is due to Ha, and it goes as follows. So we're given some Laurent polynomial f with real coefficients, some fixed degree, and a definite parity determined by that degree. We also assume that f is bounded in absolute value on T, which is the unit circle in the complex plane. Then this theorem guarantees that there exists a Laurent polynomial G, also with real coefficients. This is the complementary polynomial, and a sequence of parameters or angles phi j called phase factors, such that this equation holds on T, which is again the unit circle in the complex plane. So the right-hand side is a sequence of unitaries that you can use to implement a polynomial or Laurent polynomial f. But in order to do this, you need to first find the complementary polynomial G. And one thing we can deduce immediately from this equation, applying unitarity, we see that f and g need to satisfy this constraint. So in a sense, this is the equation that I'll show how to solve in this talk. But just taking a step backwards, the theorem on the previous slide just gives us the existence of the complementary polynomial G and the sequence of phase factors. It doesn't tell us how to find these things. So the two steps you need to carry out, called phase factor determination together. First, you need to define this complementary polynomial G, and then you need to determine the sequence of phase factors. So it's just the first of these tasks that I'll address today. Actually, I'll embed the problem coming from the previous theorem into something more general. So one thing to note is that if f and g satisfy this constraint, we can multiply them by powers of z and get a new solution. So since these are Laurent polynomials, they have terms in z inverse as well as z. We can multiply them by sufficiently large powers of z to convert them to polynomials, and then our problem is embedded into this more general problem, which I call the complementary polynomials problem. So this is what we'll solve. We're given some complex polynomial p, satisfying, so it's bounded in absolute value by 1 on T. We want to find Q with the same status, with the same degree as P, such that this equation holds on T. So we'll solve this using a technique from complex analysis. This is called Riemann-Hilbert theory. And the setup is as follows. So we're given some curve in the complex plane, some function from this curve back to the complex plane, a complex constant a infinity. So given this data, we want to find a function a, which is defined off of the curve gamma and satisfies the following properties. So it should be holomorphic or analytic on the complement of the curve. The curve will divide a into two parts, a plus and a minus. If we take the difference of those two parts as we approach the curve, we should get exactly j, which we call a jump function. And lastly, as z goes to infinity, we want our function a to go to this specified constant a infinity. So on the right side of this slide, I've got a schematic, kind of a prototypical Riemann-Hilbert problem where the curve gamma is exactly t, so this unit circle in the complex plane, and I've given it an orientation. Also, just a bit of notation. So D here is denoting the open unit disk in the complex plane. So this is the setup for a Riemann-Hilbert problem. And surprisingly, it has a solution, and the solution is even unique. So it's given by this integral formula. We're integrating this function j against this kernel z prime minus z over the curve gamma, and we're just adding on this constant a infinity. So the next thing is to relate this complementary polynomials problem to a Riemann-Hilbert problem. This will allow us to solve it. So again, this is the complementary polynomials problem. The key step is given below. So this also comes from an old complex analysis theorem called Feher-Ries. And what you can do with this is you can show that the modulus of q squared can be decomposed as follows. So it can be split into, it can be written as this product of two terms. The first, and to do this, you show that there's a parameter q naught greater than 0 and a sequence of parameters zj that live outside the closed unit disk in the complex plane. So showing this, you can write the modulus of q squares as follows. And in this last line, we can identify the first factor as q, and the second factor is the conjugate of q. So to convert this to a Riemann-Hilbert problem, all we're going to do is take logarithms. So this equation holds on t. We're going to take logarithms of this equation on t and use the fact that we have this relation between q and p. So taking logarithms, we get this equation. So we get two terms on the left-hand side. The first we can identify with a plus. The second we can identify with minus a minus. And the right-hand side we can identify with the jump function. So this is exactly a Riemann-Hilbert problem, exactly the same type I showed on a previous slide, except now we know the data. So we have this jump function j explicitly in terms of p, which is known. And to compute this constant a infinity, we just take a limit of a minus as z gets large. And so we can compute this constant explicitly. So using the fact that this is a Riemann-Hilbert problem, using our explicit solution to the Riemann-Hilbert problem I wrote on a previous slide, going through some algebra, we're able to solve this complementary polynomials problem analytically and explicitly. The idea is that the Riemann-Hilbert problem will give a plus as a solution. We know a plus is the log of q, so we just exponentiate to get q, our polynomial. So the theorem is here. There's a positive number q naught such that this integral formula solves the complementary polynomials problem, and the solution is even, unique up to a multiplicative phase and a discrete symmetry. So a good comment would be that this doesn't look much like a polynomial. However, it must be, because we know that there exists a solution to the complementary polynomials problem, and we know that the solution to the Riemann-Hilbert problem is unique. So this must be a polynomial. If we want something explicit, written in a monomial basis, all we need to do is evaluate this at degree p plus 1 points and use Lagrange's interpolation formula. And as I said before, here we have an analytic solution that goes beyond existing numerical methods in the literature, which are based on root finding or objective function minimization. So to summarize a bit, we want to implement polynomials via QSP, and we're immediately forced to consider complementary polynomials because of unitarity. We found a general analytic solution using complex analysis and Riemann-Hilbert theory. And so I've given this result in the context of this Ha formulation of QSP, but this is equally applicable to the recently introduced generalized quantum signal processing framework. And maybe as a final comment, the matrix, the Riemann-Hilbert problem we looked at is a scalar Riemann-Hilbert problem. There are also matrix Riemann-Hilbert problems, and it's possible that these kind of ideas are applicable more generally in this domain. So to give an example, you can deduce generalized QSP as a theorem by looking at known factorization theory for functions from T to SU2. So generalized QSP can be viewed as a corollary of some kind of old complex analysis theorems. So I'll finish there. Thanks for your attention. So there are good numerical methods for finding the complementary polynomial. This is mostly a theoretical result. So this is pointing out that you can compute it explicitly, exactly.